Hello again, everyone. I'm Max Herzog, a program manager with Cleveland Water Alliance, and it's my great pleasure to welcome you to the February edition of Water Data Forum. The forum is a year-long series of interactive web sessions that explore a broad range of topics around approaches to using, collecting, managing, and leveraging water data for impact. Today's session will focus on data-driven management, efficiency, and risk reductions for smart utilities. And we're going to explore this through both discussion from some great panelists, but also great conversation with the audience as well. So make sure to stick around towards the end for that. The Water Data Forum is a program of Cleveland Water Alliance, the Water Environment Federation, and the Midwest Big Data Innovation Hub. And on behalf of this collaborative, I want to thank you again for joining us on our journey to demystify water data. If you enjoyed this session, I encourage you to tune in next month for the next edition of the forum, which will focus on water equity and using water data to actualize environmental justice. You can check out the full list of sessions at clevelandwateralliance.org. We'll be sure to send out that link in the follow-up email. So if you're interested, please feel free to follow on for the rest of the year as we continue this journey. Before diving in, I want to remind folks that you can submit questions throughout. We will keep folks' audio muted just to reduce on cross chatter. But if you look at the control bar at the bottom of your screen, you'll see a Q&A option. This is where you can submit your questions throughout the sessions, and we'll be revisiting those questions at the end during the group discussion. With that, it's my great pleasure to introduce this month's facilitator, Elkin Hernandez, who serves as the Director of Maintenance Services for DC Water and is a leader in the smart water for utilities space. So with that, Elkin, I'll hand it off to you.
Well, thank you, Max. Good afternoon to everybody here on the Easter time. Well, today we have a very special panel. We have five leaders of the industry and the topic that we're going to be discussing. Keep in mind, this is about bringing together the concept of data-driven asset management, along with how it is applied to the water sector. This discussion has started several years ago, and it keeps evolving every year with the way we adopt and figure out ways of making practical and decisions with the data and the technology that becomes available to us. Keep in mind that we want to have a discussion on data-driven asset management, the efficiency and the risk reduction of smart utilities. So it goes from monitoring to response, from developing to efficiency, operations, and management. Today, we'll go to a total of 5 presentations. And let me start with the introduction to the first panelist. His name is Jim Cooper. He's with Arcadis. And Jim is an associate vice president at Arcadis and serves as the global leader for intelligent water. Jim earned an executive certificate in artificial intelligence implications for business strategy from the MIT. He's a well-established industry thought leader. He's author of more than 50 publications. Jim is also a professional engineer and serves as multiple leadership roles in organizations throughout the water sector. He's really well known in the water. And keep in mind that part of the idea behind this series that we have been working with WEF and the Cleveland Water Alliance is to be able to bring together the data world, the data experts, the scientists, and the water sector. So Jim is certainly one of a key member of that group. And with that said, I'll let him take over and present today. So Jim, please.
Excellent, thanks. So let me share my screen. Let's see. Can you all see my screen?
Looks good, Jim.
Excellent. Thanks, Max. And thanks, Elkin, for that introduction. You've set the bar high for my, my quick few slides here. So I want to spend a few minutes really less presenting and more just getting the thoughts flowing for everyone that's attending this call. Certainly, we know the topic intelligent water, and we hear topics and like digital twins and data-driven and asset management, right? But I really want to kind of get your thoughts thinking about how that directly applies to you, because I think, or at least my hope is that one of the takeaways from my few slides is that you can see that there's more to it than probably what you might be doing, and get some ideas on how you can work to improve. So first I'm going to talk about traditional versus advanced asset management. One of those topics that I think we often hear a lot about. When I talk about traditional asset management, I really talk about a focus on your physical infrastructure, right? The pipes and pumps and treatment plants, a focus on capital expenditures and how do you prioritize and optimize those. Looking at, typically to do that, you're looking at historical data or maybe even snapshots of data in time. And a lot of times when you think about end of useful life for a piece of equipment or for a pipe that's buried in the ground, most of that relies on industry standards, right? So if we switch gears and we apply some advanced technologies, innovative cultures, and intelligent water to traditional asset management, we get to what we like to talk about as advanced asset management. So there you're focusing on total assets, including people, right? The workforce as a critical asset. You're on total optimization, right? So you're looking at the O&M spend combined with the capital spend. Real-time data streams and something that continuously learns based on your data. So a lot of talk about data, right? Well, there's a lot of tools out there today that we see clients using to really bring in new data streams. And one of the things I often talk about is, what do you think about when you think about data? I think most of us today, still, when we think about data, the first thing that pops in our mind might be a Scada system. Or it might be a spreadsheet, right? Rows and columns of numbers or text or something like that. But there's certainly opportunities and applications out there where you can go much further beyond when we talk about data streams. You can have a video feed that's showing a heat spectrum, right? Or a thermal imaging in real time with machine learning that alerts you when you have a heat change within a piece of equipment or noise, right? So there's all these other data streams out there that we probably don't typically think about that are really important on this topic. So before I go through just a couple specific examples of how data-driven can really impact your utility and ultimately your people and your affordability costs, I want to talk just briefly about data, just dive a little bit into it. Whenever I talk about the topic of intelligent water, I really like to give the opportunity to get people thinking about the value of data, right? So I like this graph. It's showing basically a scale of 0 to 1 where the instance of a specific event happening, you have the absolute greatest value for that single data point, right? If we look at this graph here, we have time 0, business value 1, right, your highest. And then you have a bit of a delay in the time that it takes to capture that data, depending on your sensors and at what point you're measuring that versus where the event happens, right? And this is independent of any type of data, right? It's just general. Then you have an analysis period, right? So you've actually captured that data, it's ready for analysis. Now you analyze it to identify there's some sort of anomaly that's occurred. And then once that's been identified, then you have to take an action, right? You have to look at it and say, okay, well now we're going to decide to do something. We're going to turn a pump off, or we're going to increase our aeration to improve our DO in the treatment process or something like that. So by the time you get there, you've lost a large value of an individual data point. And there's a lot of things to think about, right, on how can we essentially, for a single data point, move closer to that one, or get more value out of the data that you're already collecting. And it's through automating a lot of those processes. So the graph I just showed you is this green line, right? We're looking at the value of an individual data item. There's also this red line, which is the value of aggregate data, right? So the larger data set that we have, the more powerful some of those automated processes, some of those artificial and collective intelligence can really provide value on, right? With a larger data set, you can, you can actually start to develop trends, develop modifying or variable anomaly detection, right? You're looking at going well beyond just the set points of a range that you're operating within to what's truly an anomaly based on everything else and all the interactions that you have within there. So I just want to share those couple insights on data and the value of it before I go through a couple quick examples. So here's an example for Los Angeles Department of Water and Power. And they were really looking to just illuminate, right? Shine a light on all these various data silos that they have. How can they bring that into a common data system, which they're using OSI Pi for, to really, again, increase the value of that data, allow their people to have better access to the data, and a number of other things, right? We've went through and identified many case studies and essentially use cases for the need for all of that data to be brought together. Okay, so I talked about intelligent water. I'm going to very briefly touch on my definition of intelligent water, and then I'll wrap it up here pretty quick. So when I talk about intelligent water, I talk about this definition, right? It's the process of water systems embracing both digital technologies and ecosystems in frontline operations and utility management, right? Two very different things there, with the purpose of doing three things. First, improving your financial stability of your utility. Second, improving the customer experience. And thirdly, improving your operations and maintenance KPIs. All of that within the basket of a cultural that's shifting towards innovation. Without that, I think you really will have more headwinds than success. A couple key things that applies across the entire water sector. It also applies to core business processes. It's really a shift away from sensors and devices, which is what I think about when I think about smart water, to the integration of technology and people, which is what I think about with intelligent water. And that includes those processing advancements, like I mentioned, right? Edge processing, digital twins, many things like that. So in my mind, when I think about intelligent water, I think about these kind of four areas, right? You've got across the entire enterprise, and then you have along an asset life cycle from planning to design and construction to intelligent ops. And you can take any of those water drops and kind of place them at any point within a water cycle. And then you can start to say, okay, well, if I want to take something like, I don't know, intelligent ops and apply that to wastewater treatment, what are the specific opportunities that are out there that I can look at my data and take a more data-driven approach and end up with something that's better off, right? Optimized, last longer, right? Any of those types of things. So if we look at collection systems and we look at that specific, the intelligent ops water drop, here's a couple examples. Capacity optimization using real-time control, pumping analyzer, where you're looking in real time at not only the head and flow curve, which is what we typically think about for a pump curve, but also the energy use along that curve, and looking at how do pumps compare to other pumps within a facility, or unit costs for energy, and looking at how you can prioritize some of your preventative maintenance practices for that. Pipeline maintenance automation, right? You can look at and identify blockages in a collection system, right? Just comparing a well-calibrated model results to what you're seeing with level sensors and things like that. If you switch to wastewater treatment, right, there's examples like process automation. I think we're well aware of the key thing that I think is important there is be tuned to the latest technology that's out there for sensors there is a lot of new sensor technology development that can feed into something that would result in improved process automation. And there's a number of examples with that you may not directly be looking to optimize a process. You may be looking to optimize a new analytic or a new data point based on new sensors, but it results many times in overall process optimization. A couple of, right, energy maintenance, predictive maintenance, reporting automation. You might think those are pretty simple, and actually they are pretty simple. Here, an example, your utility that we were working with, they had 9 different approvals that had to happen for any capital spending, right? So the primary business case to automate some of that approval process was just pure labor savings. But the secondary business case, and probably brings more value than the pure labor savings, is less manual entry errors, right? Visibility throughout the process. You can see instead of having no idea where an approval is sitting on someone's desk, you can see where it is electronically and have that accountability and history all in one quite simple site. And reuse, right? So there's a number of examples for reuse too. And certainly I don't have time to go through all this, but the whole point, like I said, is really to get thinking, what are those opportunities to improve based on the data we already have? Because many times you're not using a lot of that data, or you could be using that in new ways to improve. So we're shifting away from something like this, which is certainly, I hope, utilities are doing, right? Just a pure looking at a spreadsheet. And this is looking at pump stations and looking at their capacity versus their age versus their maintenance costs, right? And you can see when you have a really low capacity pump station with a really high maintenance cost, and that's probably not a good thing, right? We've been doing this for a long time. Everyone's been doing this for a long time. We're really switching to the topic of digital twins, right? So that we can automate these steps, right? So that we can really have a true picture of what's going on and identify those opportunities. So we've done a lot of research on digital twins and really have feedback from all of you, right? Talking with many utilities across the globe, and have identified various types of digital twins as various levels of digital twins. And I think it's really necessary when people talk about a topic so broad, such as digital twins, that you really start to peel back the layers a bit and see what's in there. You know, I've been asked the question, is Scada a digital twin, right? Well, I would consider that a digital twin ready, for example, level 0. So just an example of a level 2 twin and why someone would implement something like this. These were you know, we have hundreds of these remote PFAS treatment units, and it would take operators a very long time to drive to one, right? Just to see and get a live sense of what's going on there. So when you have a digital twin and you can actually get the correct amount of sensors in there to see, you know, is a valve open or closed, and look at those status, you can really reduce your O&M costs. And at the end of the day, that's core of what we're talking about, is how can we do better? How can we spend less to achieve those results? With that, I'm going to wrap up my presentation and really look forward to the rest of the presentations. And I think I'll turn it back to you, Elkin.
Thank you, Jim. Very interesting presentation, how to leverage technology with practical user cases for a water utility. Our next presenter is Dr. Sunil Sinha. He's the professor and director of the Sustainable Water Infrastructure Management Center for the Virginia Tech. Dr. Sinha is a National Science Foundation Career Award recipient in the area of sustainable water infrastructure and management systems. His research, teaching, and consulting activities are focused in the area of infrastructure management, sustainability, pattern recognition, sensor informatics, and resilience, especially for water systems. Dr. Sinha has documented and disseminated the results and findings from research in over 450 publications in referred journals and reports. Dr. Sinha is an authority, for anybody who doesn't know him, he's an authority on the water infrastructure at the national level. And with that said, I'll yield the time for him. Welcome.
Thanks, Elkin. Thanks for kind words. Hello, everyone. So Elkin, let me ask you, you can see my slides well and hear me well?
Yes, I do, both.
Perfect. Okay, so what I'm going to talk is, you heard the previous Jim Cooper talked about this AI, digital twin, data. So I'm going to talk the real world examples. After Flint crisis, Congress decided to have a national database of water pipeline. So the definition of water here is raw water, potable water, and reuse water, including agriculture water. Wastewater and stormwater was not included in this national project. This project started way back in 2017. So it's almost 5 years we are working in this project, and I'm going to show you what's going on with this project. Congress cannot monitor any projects, so the money came from the Congress, but the US Department of Interior, Bureau of Reclamation is managing this project. So this project, as I mentioned earlier, the title is that. So this project is also under US congressional direction. And that's why the OMB number I'm showing you is 1006-0031. We cannot talk everything about this project, but I will give you a good flavor. This project has to be, all reports has to be submitted to Congress. Once they approve, then this will come in the public domain. So 500 water utilities, I mean, minimum was 500 we need to get. And also middle map, what you're seeing is 100 federal facilities. So we did collected data from more than 500 water utilities in US and around 100 federal facilities, what you are seeing in the center. The purpose of this project was also to lay foundation for a national database of water infrastructure. So going forward with this project, if I can move my slide here. So a couple of things came in this project is that, what is the benefit to the utility? Because this project, as I mentioned you, this is a federal project. But why utility will participate in this project? And that was the key, what benefit we can give to the all participating utility. One was data. A lot of utility, they do collect data, but data is not collected as a life cycle. There is no standard definition. So that was the one thing which we wrote the report, and I will show you the standardized data. Other is analytics. There are many models and tools. There is no one model which can predict pipe is going to fail. There is a survival curve, there's a performance curve, then there's a risk analysis, and then how to visualize. A lot of utility, they do have GIS, but the challenge also is the smaller utility. And that was the condition from the federal, how to engage a small utility so that they can log in at our server. They don't need any software, GIS or any ESRI software, and they can visualize the results. So we have done all those things. So that's the key benefit we are going to provide. The other is, the slide is important. We took an approach of process-driven models. So all our modeling in this platform, what you're seeing, the Pipe ID platform, which is our database platform. So Pipe ID hosts all these data in a secured format. Utility have to log in before you get access to the database. So there is a 3-layer. There is a front website, then there is a modeling platform, and then there is a whole database. And these are secured. We follow the same like classified. We do a lot of Pentagon and other work at Virginia Tech. So all data is secured from when we get from the utility, because data doesn't belong to us. Data still belongs to the utility. So the slide you are seeing on the left-hand side, we use the process model. What that means is not just the data. If you are just using the data, then there is no system understanding. And then you are using just the knowledge that can be based on experience or heuristic knowledge. So we combine both knowledge and data. And that's where I will talk about AI. That's how AI works. I did my PhD in artificial intelligence way back in '96, I started. My supervisor did PhD in artificial intelligence 1970. So there is nothing new in AI. The only new thing is the data we are generating and the knowledge, because it's a learning algorithm. How learning will come? If a teacher is not good, there is no way learning is going to take place. There is nothing called, I mean, there is, if you look at the AI, there is a supervised, unsupervised learning, but unsupervised learning is not truly unsupervised. When they send a robot to Mars, they used unsupervised learning in the beginning, but they used that feedback loop to train that the track and the path. So it was kind of a pseudo unsupervised, not pure supervised. Other is the data. If you look at the data, when we started this project, a lot of utility, when we contacted the data, they only collect when there is a problem or they have done some inspection or failure. Even failure data is not very well documented. Some utility participated, we got really good failure data, but not all utility. The definition of failure is also not right from many utility. One utility told us, our pipe doesn't fail. It goes way past design life. So our pipe is good. We said, okay, let's analyze your data. So when we started analyzing their data, what we realized is they're right. Their pipe is not failing because soil is good, soil is not corrosive, it's metal pipe. But inside, when we did correlation analysis, we found that pipe is tuberculated. What they are claiming, 12-inch diameter pipe, internal diameter is not 12-inch. It's hardly 4 or 5-inch internal diameter. So they are better off replacing that pipe, even if it is not failing, because it's like your arteries is clogged. The pump is running all the time. It's not energy efficient. The other is, this slide is, this is the architecture I showed you, database, but any database has to have an architecture, because we are talking about national database. So right-hand side is all the modeling, different analytic techniques. Left-hand side is the way we have done analysis, local, regional, global. So the data we collected from more than 500 utilities all over US, we can do local level analysis. Local, when I say local, is a utility political boundary. Regional is based on cohort analysis. If a corrosive soil all over US, that's a regional. Global is what we are seeing all over US, the pattern, not just US, all over the world. Certain joints or certain things is falling in the same way. So that's kind of a global level analysis. What you are saying is the center one is the main where all data is analyzed. So the center, if you are asking me a question that how much miles of the pipe is in this country, we can go at the high level and do those analysis. But if you are asking a very specific question, can you tell me a cast iron pipe pre-1930, lined or unlined in a corrosive soil of medium corrosivity, how long is going to last? That I have to go down and run that analysis. So the architecture of this database is such a way that we can run up and down and run that analysis and give you the result. Lot of data we had to collect from many sources like USGS and other, because utility don't collect. In Atlanta and other places, what we saw is a lot of pipe is failing because it was a minor state and now it has become interstate highway. So loading has changed like 10 times, 20 times. So that information we are getting from the Georgia DOT and others. Same like oil and gas, railway track in Portland, lot of electrified railway track is current. So a lot of data need to be downloaded from other sources to do analysis. Now you will say, why you collected data from all over US? The reason we collected is the one condition was laid from the federal is that all our analysis has to be under statistical confidence. We cannot come and say that a metal pipe or a plastic pipe is going to last 50 years, 60 years. We have to show that based on 95% confidence. How you get 95% confidence? That you have to get from the data you collect. And one utility we saw collecting from one or few utility data, you cannot make that confidence at that level. So that's the key. So as I mentioned to you, the report has to go to Congress. We are ready to submit this week to everything to Congress, what we have found. And once they release, then it will come in the public domain. So I'm just going to give you a little bit flavor of what's coming. And all this will be free because this is a federal grant. So there are 7 documents will be coming. So first document talks about the basic understanding of the pipe, failure mode, mechanism, and all those things. Second document will talk about data. What data you should collect, time-dependent data, life cycle data, all those are written there. Report 3 talks about database management. A lot of utility, they collect and store data, but if you don't have a good database management, it's very difficult to analyze. A lot of time when they rehab, they assign a new pipe ID. So the database also plays a big role. Otherwise, you cannot do analytics at that scale. Then the fourth one is, that's where the descriptive analysis, we talked about this all typical failure mode, what we are seeing in different soil condition, what we are seeing in the coastal area, all those are reported in number 4. 5 is all the performance characteristics, how this pipe are performing in the scale of 1 to 5 all over US. 6 is basically a risk, how you define risk. Every utility has some kind of a risk, but it's not comprehensive, it's not holistic. So we looked into all literature and tried to come with a national how utility can tweak. I'm not saying whatever we are proposing, every utility still has to tweak it and use it. Then the life cycle cost. A lot of life cycle cost document is there, but life cycle cost, most of the published literature is based on design life. What we saw is design life doesn't mean anything. I will take example of, again, one pipe can last from 30 years to 150 years, we are seeing. So what's the design life here? Design life is not performance life. So that's what we have proposed in the 7.1, the report number 7. We have done a lot of correlation analysis to find what parameter is really affecting based on the material of the pipe, coating of the pipe, diameter of the pipe. This is just a flavor. We are not still allowed to show detail, but I'm just giving you the flavor. What is it? We have all different failure mode all over US, what we are finding based on, again, material, diameter, location. We are using ecological cohort analysis to mainly where soil is corrosive, not corrosive, in the coastal area, and oil and gas, and all those kind of things, because that creates a stake current. We have developed a lot of survival, thousands of them. Key is not this survival. A lot of survival curve, like buried no longer, also has the survival useful life or survival, whatever the term they use. The key is, if you look at the trend of these, some can go 80 years, 90 years, but some can fall very fast. So that slope is also very important, not just looking at this pipe the last 80 years. 80 years will go very fast from, if you look at that 75 to 85, it will go just within a couple of years. So that's kind of the key is. And as I mentioned you, the whole performance in the scale of why we can do this, the reason is because we have collected that data from all over US. Just I need to attach my. So going quickly in a couple of the slides, the risk one, we have developed this risk analysis which can be used for all pipe as a material, as a diameter. Economic analysis, the reason is, again, don't pay too much attention on the number I'm showing, just I'm giving you a snapshot. We have done for all pipe material, all diameter, based on service life, performance life, not design life. Now coming here, then I will wrap it up. I'm almost on time. So is this platform AI ready? A lot of question came there with the utilities and all those. Yes, this is AI ready. A lot of these I showed you, the previous one, these are all kind of a model and all those, but we had to do that before we come and teach machine to learn all these things. And the slide I showed you earlier, that we didn't use just the data. I will give you one example. One utility said that, Sunil, one company took our data, they use AI to predict our failure. So they took all failure record. When we looked at their data, mathematically it's not possible. Why it is not possible? Because the break pipe was laid in 1930, 1940. The break they started collecting is from 2000. It's called truncation problem. Any kind of a model you will do, forget AI. Even a simple statistical model is called truncation problem, because that is you're recording that as a first break. So your model will be biased by 20, 30 years. So we look into that. We took into consideration the model we developed is looking at all the truncation. That's why we collected data from many utility. I'm not saying it's a perfect. Still, as we collect more data, it will improve. But the good thing is we have the architecture, we have the database which can learn as more and more will come. So yes, our platform is AI ready. We are testing with 11 utilities now all over US. To make sure that model generalizes, it's not memorizing. The problem with AI is it memorizes. And there is a big difference between memorizing and learning. You don't want artificial intelligence to memorize. That's why we are piloting with 11 utilities all over US. We should be done by a couple of months. Then we will reach out to all utilities in the country, how they can use this platform to have good asset management practice. So that's all I have, Elkin. Thanks a lot, everyone.
Thank you, Sunil. That's a very interesting presentation. I'm looking forward to the report becoming public.
Sure.
All right. So the first presentation gave us a big picture of possible user cases for the water industry. Sunil's presentation provided plenty of insights on linear asset management. Our next presenter is Theresa Bruton. Will get us into a practical and actionable cases for vertical assets on the wastewater industry. So Theresa Bruton is the manager of asset management at DC Water's Blue Plain Advanced Wastewater Treatment Plant. She has over 20 years of experience in design, construction, commissioning, maintenance, and operations in the water and wastewater industries. She has a bachelor's and a master's degree in engineering. She's a professional engineer licensed in Maryland and has focused the last 5 years of her career in the asset management and reliability fields. With that said, let me welcome Theresa.
Oh, good. Had to find the unmute button. Thank you,
All right.
Elkin, for the introduction. I'm happy to be here, and picking up on Dr. Sinhal's last presentation, a lot of what he started with linear is very applicable to vertical assets, and I look forward to him doing the same model for vertical assets if he so chooses to take up the challenge. I'd love to help. So I'm talking about the Blue Plains case study of how we're using data-driven asset management. You can't start a conversation about data without talking about the people that are either using it or building it or supporting it. So I just want to take a minute to thank my asset management staff. We couldn't have done what we've done without them. They've really taken on the challenge, not only understanding the systems, but then bringing forward solutions to the end users. So kudos to them, and this is their work. So overview of DC Water. Our mission is to exceed expectations by providing high quality water services in a safe, environmentally friendly, and efficient manner. We provide water services to 700,000 people in DC, and then wastewater services to 1.6 million people in DC, Maryland, and Virginia. We have over 3,000 miles of pipe work. The Blue Plains plant, which I'll be talking about our specific asset management, is rated at 384 MGD. We've got 5,000 pieces of rotating equipment. And what I mean by that is, so like a pump or a centrifuge or belt filter press, a gate, things that move. But we have over 40,000 assets in our CMMS Maximo system because we break them down into cubicles, pumps, VFDs, piping, small piping, mostly valves. So it blooms into a lot of information, which is also a lot of data to track and manage. So our asset management really goes back to 2003 when we started using CMMS, our Maximo system. We created in 2003, but we didn't quite fully utilize all of the aspects that we could have. And then when we started trying to use the data in 2010, 2012, we realized the data wasn't put together in a way that we could really make decisions or look at it in an educated way. And it wasn't being fully utilized. People were finding workarounds. That's not helpful when the data is not there. So we looked at the taxonomy of the assets and reconfigured them so that they would make sense for later data analysis. And then redid the ISO hierarchy structure, because before it was, say, like all the primary sludge were in one location, but that doesn't really help you find where the failures are in the system. So we redid the hierarchy to match ISO, so it was more of a system-based than it was an equipment-based hierarchy. We have, as Jim talked about earlier, we have very strict workflows, and that helps us in the data analysis because you know exactly where the equipment was or where the work was in the process. And then asset criticality, it's important to realize, so we did two types of asset criticality, what I would call static and another one I would call dynamic. So we did the static one, which is you have a criticality in all 40,000 assets, and it's likelihood of failure, consequence of failure to get your criticality, but you can't change that every year because it's 40,000, it takes a tremendous amount of work. So we also have a dynamic criticality that takes into account what's currently, I guess, out of service today, right now, it's live data, as opposed to what we need for different flows and different plant conditions. So we have that rated and we use that a lot. We moved on from the organization to more sustainability. So if you don't, so QA/QCing the data, if you don't use the data and you don't QA/QC the data, then you really don't have much confidence in the data. So we do a lot around that on the data we use to make decisions, definitely. Training on our CMMS system, constantly reminding the users, because we have over 200 users adding data into the database on a daily basis. So making sure that everybody does things mostly the same way. Revolve around SOPs, management of change, making sure that the documentation that we use to make decisions also is accurate. And then improving planning and scheduling, again, making things streamlined. The more things are streamlined, the better your data is going to be, the less differences. And then the last two things, data in action and analytics. So data in action, using the data, so that allows the 200 users that are inputting the data to really have more confidence and more buy-in to what they're doing, because they're seeing it, decisions being made from it. So using that to show them their failure analysis when we do an RCM, reliability centered maintenance, and how do you change the way that you're operating or maintaining it in order to make the equipment more reliable, or change the equipment for that part. KPIs went from an Excel version to when we were doing more business analytics, to more the concept of data visualization and digital storytelling, not just giving somebody graphics, but then actually we're walking them through, and then in a way that they don't have, if they have a question, they can answer it within the live report that they have. And then risk analysis and capital planning, really on the business intelligence side, kind of moving forward on that perspective. Our business case for moving from just taking data and looking at it is really just that concept of moving away from spreadsheets and into more of a graphic that people can understand quickly and not have to or spend time trying to figure out what you're trying to tell them with these really static one-dimensional Excel spreadsheets. And then we, in line with trying to QA/QC our data, sometimes you would have to log into multiple different data sources to find out what's right and what's wrong. So we would have to look at what's out of service in our Scada PCS system and then compare to what's out of service in Maximo. And that was very labor intensive. And then just seeing the relationships in the data was difficult. Maximo is a great background, but sometimes pulling that information out can be challenging. And not everybody has access to Maximo or wants to look at Maximo. So how do you have a platform that everybody can look at that's not painful to go through? And then again, the ISO hierarchy is wonderful for looking at relationships and information, but Maximo didn't quite do that very well. So our design for business intelligence are really to have an interactive database, not just an Excel spreadsheet that you get, but something you can use the hierarchy to drill up and drill down, to roll up costs if you want to see a higher level, but then also drill down if you want to see which specific pump is causing the most problems. And then drive behaviors. So if you show how reliable certain trades or certain departments are, then it kind of drives a competition between different, with 12 mechanical, electrical, reliability, and instrumentation shops. So between the 12 shops, really drives a behavior and a competition between them. And then reducing risk. If you can see the lagging and leading indicators, you can make a decision. And then automation, keeping it simple. I don't want to do any more spreadsheets. And then drive decisions both on the maintenance and capital planning side. So this is sort of our formula for how we hit our target and what we did. So looking at the tools, we tried Excel, that was clunky. We tried business objects, that was really difficult to use. We're currently using Microsoft Power BI. It's very easy to use. We really like it. Data infrastructure, having clean data and having organized data is important, and also having an infrastructure so that you can bring things together. And then IT support. We had a great relationship. We have a great relationship with IT. They trust us, we trust them. They allow us access and allow us to do things without having to constantly ask them to do it for us. So being able to do things on our own and understanding the process and understanding the people inside as the users has been very helpful. And then talent, I showed my staff at the very beginning. I can't tell you how important it's been to have the people on the front line that understand the process to be able to match those things together, and they understand how the data works and the process and the QA/QC. And then user buy-in, not providing people with graphics because the industry says so, but answering a question with the graphics. What are the directors and the managers? What questions do they have? So for example, we used to give the general foreman 70 pages of work orders. Well, nobody's going to look at that. So designing a system that was easy for him to quickly make decisions and run the plant. And then I've heard of the 1-5-10-minute rule. So having a report that in 1 second, the executive can see the dashboard and understand things are good. 5 minutes, the director can do one level down and kind of see where he is. And then 10 minutes, you can say the same report and drill down, and the manager can see what area specifically is going on in his or her department. So data visualization, I've seen this type of slide multiple times where all these different databases come together in one spot and then it creates the report and make decisions. I couldn't quite figure out how to get everything together. And the challenges we had with this was our Scada system was designed, everything's named by the points in the system. Maximo is designed by asset numbers. So we actually had to create create a connection between the two, taking all the points and all the assets and linking them together, which can be very labor intensive. And then our future is to link the predictive technologies, both the IoT ones that we have in the field, and then also the measurements that we take. The challenge with that is it's separate outside vendors that want you to go to their website and look at the data and not give you the data. So that's a challenge that we're currently looking forward to. And then creating a report, and then making business decisions, capital planning, obviously future investments, how is that being driven? And then the 3 cornerstones that we built off of for maintenance decision making, for budget, critical equipment, and predictive maintenance, proactive maintenance. So I'll show you 3 examples of those. So for our maintenance, we created this, there's several different budget type graphics that we have. This one specifically is for what parts are we buying. So you can see we buy a lot of kits and screens on the left-hand side. On the bottom, you can see what you're buying and what work order and how many. And in the middle, you can see what plant area is costing you the most amount of money. So the top is Class A biosolids, night, headworks, plant chemicals, and it just automatically jumps out at you. Wow, Class A biosolids, it's expensive. And then you can actually click on those colors and drill down and find out which piece, how often. And that's driven a lot of management of change on the material side for us. We've changed multiple materials of construction, changed some of the processes, redone our PM program to try to drive that down and find out where it is, or show our finance and say, this is it, this is what it actually costs. I've heard that $1 in design actually equals about $100 in maintenance, and this really drives the point that how much does it cost to actually maintain the equipment? And then from equipment availability, so the middle graphic is the pie. You know, what is your red? What is your immediate concerns? Is that greater than 5% or lower than 5%? And we have a very conservative number that even if 3% of our equipment is red, you still have time to react, but you need to act quickly. So sort of gives a visualization, and then you can click and it can tell you which equipment, where it is, what work order, how old is it, what status, who's in responsible. So you don't have to go into Maximo and find these things out. And then you know immediately what's your risk to the process, just like you know your risk to the budget. And then tracking reliability, again, this is more of a proactive, showing what you're trying to get people to be more proactive. And if you show the numbers and you measure the numbers, then you're more likely to get this. And then it also drives, you can look in specific areas or equipment or shops, and it kind of drives also where you're trying to focus your energy on projects and changes to get things done. And then in conclusion, we found that Power BI is a very easy tool for us to use to interact with the data. And even the sources that we've connected, even since then, we've connected the lab data to Power BI, document management, Seek, which is our process side, looking at the process equipment and how it's doing based on the flow and how it's operating. And then our biosolids is also connected to Power BI. So everything is in one spot that you can pull and look at the information. And then driving KPIs that are, again, data visualization and digital storytelling, really trying to get the information out, because there's so much information out there, but how do you understand it? How do you communicate? And how do you make a decision from it? And then just driving other programs. Using the data means that it's more likely people care about it. It's going to be better data. So for not financial analysis, KPIs, driving capital projects, I can now show the capital group things are failing and how much they're going to cost. And the next step, just continue to find opportunities to create actionable data. So thank you.
Thank you, Theresa. Appreciate the presentation, and certainly having enough data and data of good quality makes decision making much easier and help us to avoid risk. Our next presenter is Mr. Guy Meiri. He's with IOSight. Guy is a seasoned business development professional with over 20 years of diverse experience in strategy, business development, and management. Guy joined IOSight in 2019 and leads the business development of the company's water-specific data management and analytics solutions in global markets. Guy has worked for leading companies on different sectors, focusing on digital data and analytics innovations and programs, including the development of businesses for robotics and cognitive automation practices. So Guy brings something very interesting to the water sector. His experience from other sectors through his career, and help us to with the idea of being able to leverage that knowledge into our own challenges. So we thought it was a very interesting point of view and added value for this panel. So with that said, I'll yield the time to Guy. Welcome, Guy.
Thank you very much. Thank you for your kind introduction, and it was very interesting to hear the other presentations. And I will share my screen. Sorry, just a second. All right, please just confirm that you see the full screen. Can you see the full screen?
Yeah.
Yep, it's coming through, Guy.
Yes, we do.
Thank you very much. So thanks again. It was very interesting to listen, especially to the last presentation by Theresa. I was just thinking about, I wish we met, before you started your project. But anyway, so I'm going to talk about what I call the 4 pillars of data-driven asset management, and it's a completely, subjective, I would say, perspective. It's like not the truth. It's like my perspective, and as I mentioned, I've been with a company, actually with the industry, for only 2 years, but I do bring perspectives from other sectors, from other domains. So that's my kind of like combination of experience, and within IOSight, within the water sector, and outside. So a little bit about IOSight. What do we do? We are considering ourselves a leading provider of data management and analytics for the utilities sector, mostly water, wastewater, and the entire water cycle. Our team is a combination of engineers, process engineers, water engineers, environmental engineers, a software development team, and data scientists. And we have over 100 installations worldwide. We've been operating for over 10 years. If you look at some of our clients across the sector, this is just like one way of looking at the sector. So we look at, we serve water and wastewater utilities and facilities around the world, in Israel, the US, China. So for example, in Israel, the city of Chicago Water Department, Las Vegas Municipal Water District in California, working with Southern Company on the water operations. In China, BWG. In Israel, Mekorot. Desalination is a very big sector of ours. Israel's potable water, 80% of it comes from desalination. All 5 desalination plants in Israel use our system, as well as the Carlsbad in the US and several others. And also watersheds in the environment, real-time water quality monitoring in the Jordan River, also doing a project in Chicago, HTML Chicago, and several others. So we have a broad perspective on the water sector, and what I'm going to share with you today mostly is some I would say, I wouldn't say anecdotes, but examples, combined with the with the perspective. And obviously we realize, we learn that data has the potential to improve almost everything which is related to resilience and performance across the water sector: water quality monitoring, access to clean water, operational efficiency, reliability and minimization of downtime, which is kind of like the heart of what we're speaking about today, affordability and environmental protection. The problem is that there's a lot of data, as we heard, but it's difficult to turn it into actionable insights. Not just insights, but actionable insights. Because there are diverse systems, again, like we heard, there's the Scada and the LIMS and the GIS and many other systems that are kind of like, and CMMS that kind of like need to work together. They're not synchronized, and sometimes it's really difficult to drive decisions, and most of the time out of that. And that's exactly where our system and our experience comes to play. We take in the data from all those diverse data sources, like I mentioned, the OT, that's the Scada, operational systems, laboratory, GIS, and all the rest of them, and manage them, store them, manage them, treat the data, and then serve, provide outputs that I'm going to show you some example of those, like reports, dashboards, analytics, and so on. Basically enabling true data-driven water management. And specifically today I'm going to speak about, before that, especially last year, we felt it, everybody felt it. It's critical. When you're away from your facilities, when you're at home, you need to be able to maintain business continuity, do it in a comprehensive way, in a convenient way, and to collaborate. So this is the new normal, and probably going to stay with us for a while at least. And we've delivered the entire project. We worked with teams that were never on site. And what you see here are just two examples. The dashboard, our dashboard at the home of the operations manager of one of the desalination plants in Israel, and mobile dashboard of the watershed management, and again in Israel. So this is again emphasized the remote, the ability to access everything remotely and securely, obviously. So when I deep dive, dive into the specific topic of data-driven asset management, the way I look at it is like 4 elements. And again, might not be the truth, the Bible, but it's my perspective. The first thing is the data foundation. How do you make sure that all the data, the relevant data, is collected, and only the relevant data, and it's also reliable, clean, well modeled? That's the top left side. Then you can just start getting insightful outputs just from simple dashboards, reports, or data investigation. So you don't, before you even start analyzing the data, how can you get just insights out of the data that is already there? The third layer is the predictive analytics. That's already the more sophisticated prediction, anomaly detection, early fault detection, predictive maintenance, optimization, all these sophisticated analytics. Sometimes you can call them AI. I like just to call them predictive analytics or advanced analytics. And the last layer is the last component is the prevention and response, what makes the system operational. Working with real-time data, making the most out of it, the insights, predicting, but also acting in real time or acting in a timely manner to prevent or to respond to events. So these are the 4 pillars, and I'm going to show you some examples from our experience, and just follow those little icons for each one. So the first thing is the data foundation, making sure you have a good set of data. So we use pretty robust cleansing and validation methodologies, pre-processing, normalization, data logic rules, sanity checks. The example you see here is a recent one. This is a tank level chart. So this is what happened last month. And suddenly we realized, or the client actually realized, that all those drops to 0, which doesn't make sense. Tanks don't go up and down like that. So we applied some of our rules to eliminate that, getting to this normal picture. I would say it's even going up to the 10. So this is just with one simple illustration. You need to make sure that the data you have is correct. This is a simple one. You might have not seen it. You might have done averages based on false data. Critical. Making sure you have reliable data. Second one is the modeling and virtualization, meaning that you need to store everything in one platform, everything under one consistent, coherent tree with the right hierarchy. So all the data from the various data sources mentioned all in one place. The engineering product tree. Some of the data, some of the tags are virtual tags, like calculations, not the raw tags. So that's the second thing. This is the data foundation, making sure you have meaningful and reliable data. And then you can start looking at dashboards that you have for the real-time data coming in. So for example, you can see here two kind of like trains in a desalination plant, and you can immediately see when you look at the energy consumption that there's a difference between the two of them. And in one of the trains, you see clearly a difference between the two pumps in it. So just the difference between the two trains and the pumps inside each of those can really can indicate to the maintenance team where they need to focus their attention, just like looking at the data. This is simple. The same thing goes for pump vibration, for example. You look at the data, you see there's a difference between the two trains, the north and the south. You also see that within the south one, there's clearly this yellow one, this pump number 8 is not normal, it's high. So now you need to know that there's some sort of problems in the vibrations there. Again, the maintenance team can decide to allocate their attention to that pump or that train. And that's just, again, without any analytics, but you get high quality, reliable, real-time data on a continuous basis. The same thing can also, the same insights you can also drive out of reports. You can see in a report, which is being generated automatically, that the temperature here is very high. It's an anomaly, clearly indicating some sort of a problem with this pump. And again, focusing your attention to treat that pump, even if it's outside your regular schedule, just based on looking at this data. And also the same logic could apply to energy consumption, which may indicate a block or a high level of saltiness, which can indicate some sort of which can lead to higher chemical consumption or energy consumption. All these things just by looking at the data, the visualization, and the reporting. The next step, which is the kind of like the right-hand corner I showed, the predictive analytics, you already take the data and start analyzing it historically, and you analyze it historically, and then you predict all sorts of events. So this is looking at stuff which is not under the spotlight. We now looked at the spotlight, but now you're looking at data which is not, or trends or anomalies which are not highlighted under the spotlight. So one example, which we're dealing with right now, we have two projects actually with desalination plants in Israel about predicting pump breakdown. So we're looking at booster pumps, and we're looking at vibrations and temperature data, studying the curves, what's normal, what's expected, what's kind of like outside the normal, looking also at all sorts of seasonal attributes to kind of like make sure that we normalize the analysis and find relations between the parameters. The idea is actually to predict when a pump is going to maybe break down and respond to that. Another type of analytics is around optimization. You can, based on historical data of the operations and demand data, optimize the operations of pumps or blowers and the wastewater treatment plants, or chemical dosing. This is another one of our solutions, and save energy and chemicals up to 10% based on our estimates in water treatment and wastewater treatment plants. This is different. This is a different type of analytics. It's the optimization. If you go to the operational kind of like level, it is about actions. It's about activities. For example, maintenance management, a very simple one, managing correctly maintenance tasks and doing it in a convenient way based on data that's already stored well. So here you can see our maintenance management dashboard and scheduler, and also the mobile interfaces for reporting a breakdown and managing the routine tasks. Like you can see here, actually, the routine task management and exception reporting. Very convenient, very operational. This is how you turn the data into actions, okay? And also the last one, which is maybe more interesting, is the event management system. Part of our iGreen platform includes a rules engine and an event management. So the rules, basically you can define rules for regarding warning limits or critical limits of certain indicators, like it could be water quality, pH, but it could also be the outcome of an algorithm. For example, the integrated water quality index that we have in certain cases, or something else. And it can tell you if it exceeds a certain threshold, please send an alert. Or not please, it does send an alert with a push alert through text or email with reports, and you can manage those events on screen. Again, this is something, you take the data, you analyze the data, but you turn it into action, into response. So this is, again, the fourth component. So if I summarize our view and our experience of the four pillars of data-driven asset management, you start with creating a robust data foundation, reliable data, meaningful data. You don't need the 40,000 tags you have in the Scada. Maybe 4,000 are enough for you. Then you just start looking at the data on a daily basis. Sometimes 10 minutes in the morning. A very good friend of mine used to be the general manager of one of the largest desalination plants in the world. He says 10 minutes in the morning, looking at the reports in the dashboard, he already knows what his day is going to look like. Look at the data, insightful outputs. The next thing is the predictive analytics. Predict, detect anomalies, perform optimization of reduce energy and chemical consumption. Okay, that's the analytics. And the last one is the prevention and response, act on the insights. So the event management or preventive or maintenance management modules, which allow you to actually manage tasks. So I think I'm okay within like my 15-minute limit. Thank you. Happy to answer questions if you have. And
thank you, Guy. Thanks for the presentation. So we have the perspective of a technology provider, and hopefully that helped us to build in the knowledge that we are getting through this session. We have one more presenter before we open the door for questions. Our next presenter is Mr. Tim Stothards from Eramosa. Tim is the co-founder, board chair, and current CIO of Eramosa, a consulting firm working with municipal partners across North America to provide technology solutions. These include process control and automation, system integration, asset management, data management, IoT, IT, network, electrical, and control systems. Tim was part of the team that built Iris. It's a data management, analytics, and visualization tool. Important to notice that this tool came before the topic was popular, so they were really pioneers on the innovation on the water sector. Currently, Tim's interests and his company's interests are into the digital water solutions and smart watering technologies for looking for applications such as detection of leaks, burst, pressure monitoring, pressure transients, and water temperature, all in the context of the water distribution systems. With that said, I'll turn the floor to Tim. Tim, welcome.
Great, thank you very much, Elkin, and thank you to our other panelists who shared their experiences. If I just take a couple minutes to recap, Jim started us off thinking about how we value data and how do we maximize that value, and also some definitions around intelligent water, and also looking at digital twins from different aspects. Then we switched to case studies such as Pipe ID, which we realize is more than just a question of pipe material, there's soil conditions and that. It's really a data question, and then how we actually implement AI and machine learning to generate meaningful results from that data. And then Theresa shared with us a case study at Blue Plains plant, talking about data access, data quality, and applications that they're using. I love the idea that data in action only actually occurs after those other building blocks are in place. And then Guy's perspective on the four pillars of data-driven asset management, from data foundation and validation to beginning with insightful outputs and finally predictive analytics, and ultimately prevention and response that hopefully lead to a saving time and money in our operations. So now I'm going to take a little bit of a journey to talk about some need for strategic alignment on our digital journey. talk about data like the other panelists have, and maybe just reiterate some of the points that are key to achieving a utility that's into data-driven asset management. And then also look at a couple case studies and talk about how we might consider our next steps as a utility. So jumping in, I'd like to start by looking at the attributes of effectively managed utilities and the keys to management success in terms of positioning the discussion around data-driven asset management. So you'll notice on here that I started to put some numbers on. And of the 10 attributes, I've actually highlighted on the inner circle 6 attributes that jump out as being an area where data-driven asset management would be applicable. After Jim's discussion, I have no idea why I didn't include financial viability on this one. So we might as well call it 7 while we're talking about it. In fact, all 10 could be seen to be key elements in terms of your asset management strategies. On the outer ring, all 5 of the keys are part of asset management. Whether we're talking about knowledge management or measurement or continual improvement, at the end of the day, we need to start somewhere. And it can be overwhelming when we look at the effective utility management framework. But just so you know, for those of you who are not aware, there is a self-assessment tool on there that comes with the primer that can help you get started on this path. And as you start to strategically think about how data and asset management come together in your utility, you can reference back to this model in terms of thinking about attributes that are important to your utility. When we think about it, often the case, each of us needs to determine where we're at in our journey. We need to consider people, obviously, process and technology. So when we're considering our people in particular, we need to think about the impacts of change management on them. When I think about Theresa's example from Blue Plains, she mentioned the team of people involved, but there'd also be many other people who are involved daily in operating and maintaining equipment that are going to be subject to some sort of change as we move towards data-driven decisions rather than industry standards or elapsed time for repairs and replacement. The other thing we need to think about is strategy alignment. How do we align our utility around digital? How do we align it around asset management? What is the purpose of asset management for our utility? How do we frame it in terms of our business goals? What are our goals as a utility? Maybe hearkening back to the EUM leadership model and looking at ways we can integrate that. Finally, do we have a digital strategy? If we don't have a digital strategy in place, we might be too early to the game to really leverage data for data-driven asset management. Then obviously, as we move from people, we need to talk about process. What are we doing for asset management today? Have we actually defined our assets? Do we actually have a core understanding of what it is we're trying to manage? Is it pipes of a certain diameter? Is it vertical assets? Is it buildings? Is it pumps that are over a certain horsepower? We really need to get a grasp on the actual assets and how we're defining assets within our utility. Then we need to look at solutions. What solutions do we currently have in place? Do they make themselves amenable to data-driven solutions, or are they old cards or Excel sheets or other things that are going to be harder to integrate? Finally, we need to think about effectiveness. How effective is our existing process? Maybe before we dive into data-driven asset management, we actually need to really visit our process of asset management to make sure it's in alignment with the way we want to be doing business going forward. Then we obviously have to jump and start looking at technology. When we think about technology, I immediately jump to data. This is about data-driven asset management. So we've already heard about data and the challenges. What is some of the things we need to ask ourselves? Do we have available data? Do we understand the sources of data that we can use for asset management? How do we validate, or as Guy said, QA, QC the data that's coming in so that we're not making decisions based on data streams that are erroneous? Also, how are we going to automate and integrate all of these different data sets together? We heard about Power BI, Elkin referenced ERIS that we were a part of. There are different solutions out there that help us integrate and automate the processing of data as we move it forward. So remember, it's also about people, process, and technology. Data-driven asset management is not just a catchword that we want to jump into without thinking it through properly. Now I want to jump back over to the digital twin. Jim introduced digital twins in his discussion. One of the ones he talked about was an asset health twin. So what I've done here is I've actually taken the smart water network model for digital twins. And you can see here that as you move from left to right, you're starting with the physical system, then sensing and control. We have data collection sources. We have the area that's sort of referred to as the digital twin, which includes data integration, analytics, and visualization. And then we have all kinds of user experiences where we're learning from the data and we're making decisions and informed choices. So when I think about it, I sort of look at assets that actually exist across the organization. So the assets don't only include your physical assets in the field, they also include your technology assets. Oftentimes we forget that technology and data providing assets are actually assets that we have to account for in our management plans. But I've sort of divided it here. You can see the line breaks. We have the physical system assets, sensors and actuators and equipment. And then we also have the data collection and the technology components. Then you need to look at your data sources. Do I have the right data sources? Are they going to be able to provide me with the right data to actually drive asset management with that data? And am I actually collecting it in a way that makes sense? You know, we talk about spatial data. So do I actually have it spatially located so that I can easily access it through different platforms that are geospatial in context? Do I have it, and we heard it said, are they tagged in a way that we can link them? Or is my CMS system and my Scada system working on two different tagging systems? So there's a lot of work to be done with data before we can just quickly turn it into driving our asset management process. Obviously, the whole data handling. So this part of the digital twin talks all about data ingestion and integration and management of data and how we actually handle the data. How are we handling data in terms of, are we integrating silos together? Are we building data warehouses? Are we putting it, Jim gave the example of sort of shining a light on our different data sources in his introduction. Are we shining a light on the data sources so we understand them? And then do we actually have models in place to be able to leverage the data? So what applications are we going to use going forward? So not to dissuade people from heading down this path, but recognizing that heading down this path is more than just a quick decision to adopt a single technology and call it done. I like to think about data this way. In terms of data, we have this massive data lake, and data is coming at us from all sorts of different systems. The question becomes, how do we actually pull data together? It doesn't matter whether we're doing it for operational KPIs or data-driven KPIs around asset management. Ultimately, we're looking to use data from across the entire utility to make these decisions. And you can see in this example that we talk about disparate data systems. We talk about joining the data, symbolized here by data being pulled out of this data lake and sort of summarized into groups that make sense for us. One example, and these are just 5 data sets you probably have: Scada, CMMS, financial, GIS, external data sets that might come from IoT platforms, environmental platforms, all sorts of other things that can feed into your learning here. Also, there are other data sets I didn't even mention, like laboratory data sets. So remember that you need to shine that light, figure out your data sets, figure out the important data for what you're trying to achieve on this journey. Now I'm just going to look at a couple quick examples. This is an example where equipment had been installed back in 2008. So what you see here in 2008 is the original installation of a pump. You can see the data from the pump. Here they're looking at amps versus flow. So really, how efficient is my pump performing? You can see that in 2008, when they implemented the pump, they made some sort of operational change early on. There's a shift. And whether they went from right to left or left to right on this chart, I'm not clear. But what you do see is in 2018, so 10 years later, there's a clear loss of efficiency in the pump's performance. By bringing together other information, such as work orders from your CMMS system, what we're actually able to do here is identify a piece of equipment that is degrading over time. And maybe we start to make decisions about the maintenance we perform on this piece of equipment based on limiting the lowest efficiency we allow it to achieve. And that means that we're going to save on energy. We're going to produce more flow for the same power. it's a great way to just quickly think about it. So this is really just being able to look at data. This doesn't really require any massive analytics. This is just visualization of data sets that make it more informative to us to make those decisions around our assets. Another example, and this is a dashboard that's looking at an alarm management dashboard based on the ISA 18.2 standard for alarm management. But here we're using data from the Scada system to identify alarms and failures within the water system. In this utility, they're also looking at their wastewater system. It's a joint system. But starting to use that data to understand the assets that are more likely to fail frequently. Which ones are creating alarms on a regular basis? Which ones are going down? Which assets are online more often than they're offline? And which are offline more often than they're online? So we have some key assets in all of our utilities. And it's really important for us to understand the value of having those assets available. And one way to do that is to look at the impact on our utility of downtime of our assets. So when things are failing and alarming and creating work orders, it's really important to get a handle on that. This might also allow you to drive purchasing decisions at your utility. If you can clearly show that the failures for equipment of the same age occur much more often on product A versus product B, this allows you to make more informed decisions about purchasing decisions in terms of model, make, quality of the products that you're looking to install. So this is just another example of using data to inform your asset management decisions. And then finally, before we go into discussion and answer questions, this is just using data to create management KPIs. And we talk about data-driven asset management here, but also data-driven utilities. How are we putting the information, as Theresa said, in a 1, 5, and 10-minute report? Are we looking at it from a way that somebody can get a quick, high snapshot view? And if we're thinking of it that way from an asset perspective, something like water consumption, energy consumption, natural gas consumption, compared to our KPIs in a quick format like this, can give you that immediate snapshot and then allow you to drill down for further details and information as you go forward. So thank you for the time. Thank you, Theresa, for showing us some great examples of the asset reports from DC Water. It certainly helps us understand the context of how you get from data to information that can be used by people. And Elkin, back to you to head into our panel discussion.
Oh, thank you, Tim. Wonderful presentation. So folks, so these are our 5 presenters. Now we have time left. We have about 35 minutes, and we're going to use them to go over a couple of preset questions, and as well as some of the questions we're receiving through the chat. So, so first of all, thanks everybody. I hope this provided a very well-rounded vision of the asset management and where we are today with the utilities, within the water utilities. And for anybody who's familiar with the topic, will know that every year we're changing and we're finding what really is more appropriate for our industry. I want to share the first question with the group, and please feel free to discuss it. The first one is, what do you see are the biggest challenges or roadblocks to intelligent water and data-driven asset management?
And I can take a first shot at that.
Please.
So I think there's, if I were to identify it, there's probably 2 of the biggest challenges. Most of the time, what we think about is challenges are not actually the challenges. So it's kind of flipping it on its head, but there's been a lot of surveys and research done that found that people are actually the biggest challenges to adopt this in culture, right? So, how many of us had the ability to do video chats and conferences and turn on our webcams when we have webinars like this, right? That's been around forever, and it took a pandemic for us to actually move to actually start doing that regularly. So, it's really looking at what's stopping you from doing it, you being you personally, and then how do you get over that to get to the next step?
Elkin, I can add.
Sure, please.
Sure. Yeah. So let me put from the science point of view. I feel the biggest challenge, especially working with the Pipe ID project when it came to collect data from 500 water utilities all across US. One thing I face, the biggest challenge I face is this water sector, they don't have a standard. Most of the bigger utility, they said they have GIS. Units are not same, coding is not same. So it's a lot of manual work. I mean, it took us, 5 years. I mean, people will ask why it took you 5 years to develop all these analytics and all those. Lot of 80% went in manual work, data cleaning. And definition also, a lot of definition is not right. Failure, leaks are not defined in a standard way. So I feel if we are going for intelligent water, first of all, we need to define what intelligent water means. But if we are talking about more artificial intelligence and all those, AI will not work, as simple as that. AI need a good data, structured data, and unbiased data. A lot of issues with data. Data is not black and white. A lot of time people don't understand, they don't have time-dependent data. They have only one shot or two shot of data, and they want to develop to predict when the pipe is going to fail. I feel that's the biggest challenge in this water sector.
Thank you, Sunil. So it's very interesting that you made this comment. One of the questions we have in the chat is directed to you, and it says, when using data from multiple entities to build a more robust or reliable machine learning or a statistical model, how do you get around the possible challenges of local factors that might be highly influential?
Right. So yeah, this is a very good question. And this is what we struggled in the beginning, that how you create, I mentioned in my slide, we did a lot of cohort analysis. You cannot do cohort analysis like in a medical, they do cohort analysis. There's nothing new in cohort analysis. But medical, they have a very standard all over the world. When they do X-ray, they have a standard how they do X-ray, right? So you can collect those data from all over the world. And AI is very data dependent. To answer the question, we also tried to use a stratification method. What is a stratification is we didn't take cast iron pipe and say, okay, we will take all data from the entire 500 utilities, cast iron pipe, and put it in one box and do analysis. No, we did a stratification, cast iron pipe, pre-1930, line on line, different diameter. So one slide I showed you may not be, because of the time, we went very fast. The whole architecture of that database is stratification. Now, the challenge is in stratification is when you stratify like cast iron pipe, pre-1930, highly corrosive soil, sample size start reducing. And that's where the confidence, I think the person asking this question is that how you make sure that it matches with the local. So we tried to match with the local scenario. So what we did is we didn't just take the New York data and try to match with Boston or try to match with Los Angeles. We tried to take particular material, the soil condition. Soil also, is it corrosive? Corrosive also going into more detail, whether it is a steel corrosivity or concrete corrosivity, like those kind of things. So stratification played a big role in our statistical analysis.
Thank you, Sunil. I think we can move to the next question. It says, what are some of the key steps toward creating a data-driven asset management environment within a utility? Tim?
Thanks, Elkin. You know, I think one of the challenges we have, we hear this digital promise, right? Digitization, the digital world is going to solve all our problems, and we throw around a lot of acronyms, you know, whether it's AI, ML, BI, but ultimately, if we are going to succeed, we actually need leadership to lead us through that digital journey. We need people who are willing to take on responsibility for seeing the transformation of the utility. It's not that it's going to be easy, but I think you need to start with a strategy around digital and what you hope to achieve with that digital strategy. And then from there, you start to roll out questions about your data, questions about validity of your data, questions about applications and tools and that. So I think really you have to start with leadership. And I always come back to leading with a clear sense of where you want to go as a utility in the digital journey is going to make it much more achievable than if you just jump in with both feet.
Yeah,
Thank
and
you.
I will also add here, my thought is when you take ownership of physical asset, try to take ownership of digital asset also right from the beginning. Because a lot of time we have seen that the utility data is only when there is a problem, then they went and inspected. It's the same like human health, right? You cannot visit a doctor once and think that that person can diagnose in a better way. Baseline data is not there. Most of the baseline data doesn't exist, especially for the pipeline.
Thank you. Thank you. Thank you for your comment. I'd like to, we have questions coming, so I'll try to leverage them with the discussion. There's a very interesting question, and I'd like to hear thoughts, especially from Jim, on is there data that utilities should be collecting but are generally not collecting today? What would be your thought there, Jim?
Yeah, absolutely. So it's actually a really good follow-up to this question on what are key steps towards creating this environment, right? You know, across any spectrum of utilities that we worked with, whether it's a small utility or the largest utilities across the country, they all say the same thing. There's some data out there that we should be collecting that we're not, and we're collecting a lot of data that we do absolutely nothing with, right? So, you know, the data that you're collecting and you're not doing anything with, that's really you really need to evaluate, well, why are you collecting it? Because certainly you're bearing the cost to maintain the equipment, to transfer and communicate the data, to have the storage capabilities, right, for all that data. So, you know, so that's the one spectrum. The other side of it is what data are you collecting that you should be, right? And it really depends on the utility. Obviously, there's a ton of different data streams out there, but the step to answering that question is to do a bit of just a benchmarking exercise and a road mapping exercise, looking at the data that you have and identifying who uses that data stream. Why are they using it? Right, going back to the value I was talking about, what is the value of that data versus what it takes to collect and maintain that equipment? And you can really start to get some insights into exactly what you're doing with that data, why you're processing it, and everyone, you know, typically that's happening within an asset management role, you learn quite a bit too. You learn how your operations are using data that you may not know otherwise. So that's really the first step, is to look at what you're collecting and kind of develop what those connections are across your utility.
Thank you. A very interesting question just came. It says, a major challenge in developing predictive models is the availability of data and data sharing with researchers. The questions, I mean, certainly is directed to to Sunil, is will the data collected be anonymized and shared with researchers?
Oh, right. That's the plan is. We haven't done because this is still an active project, so we cannot do it right now. But that's the plan. The bigger plan is that to sanitize, because we cannot expose any utility. As I mentioned in the beginning, data still doesn't belong to Virginia Tech. Data still belongs to the utility. But if we sanitize these data, and medical community has done this, so that we are hoping to do it next year, not this year, because this is still an active project.
Thank you. Theresa, I have a question directed to you. It says, can Power BI be used, applied with data located in various cloud services, or only with Microsoft OneDrive? This is very technical, but I thought it would be interesting to try to answer.
Yeah, so I just looked up in Power BI. It can pull from any of your databases, whether they're on the cloud or in your servers, as long as you have access to them. So SQL databases, Oracle databases, SharePoint, Access databases, SAP, Internet, online services, Azure databases. There's a lot it can connect to. And if you're doing sort of SQL statements in your Max mode, trying to pull information the old way, if you have access to pull SQL statements, you will have access to pull it in Power BI. And you can also pull data in with the tables, or you can write a SQL statement and pull it in that way. So it's multiple different ways you can pull the information in.
I think certainly these tools have been evolving they're evolving very fast, very quickly, especially over the last 4 or 5 years. Certainly, I myself witnessed how a tool like Power BI went from having limited connectivity to being very flexible. And I think this is true for other available tools. Be careful not to try to advertise just one. But I think most of the providers of this type of tools they understand that flexibility and connectivity is key for them to be successful. I have another question that is, I think, find to be very interesting, and I leave it open to everyone. All these tools seem to be targeting larger utilities. Do you have any recommendation on how a small rural utility could start digitalizing and get the benefit of these tools?
Maybe I can take that. I think it's a very good question. It's challenging for smaller utilities, but we've been working with medium to large, but also like not so big. I mean, even the one that we're working with in California or others in Israel that are like, some of them are rural, some of them are municipal, but not the large ones. And I think in that case, you need, again, I'm biased, okay, obviously. So, but I think you need one good platform that already has all the connectors, that already has all the connectivity. You need a good methodology to decide how to start. You need a good methodology to decide. People talked about it. Which data do you need? For sure, Jim said you cannot start just. You need to be very focused. Okay. Sometimes one idea that we thought about was actually to combine several utilities together, smaller ones. So I think you need to be very selective in how you choose your platform and how you do your design of what you want to achieve: water quality, protection, efficiency, and things like that. But it's definitely doable for even for smaller utilities. You don't need hundreds of thousands of dollars for that, for sure, in my perspective.
Right.
Anybody else?
Yeah, Elkin, yeah, can I add? This is very important question, actually. This was the condition laid by federal government when we got this project, Pipe ID. How you are going to engage a small utility when the resources are very limited. So what we are doing now is, in the beginning, when we started this project, we didn't engage a small utility for a couple of reasons. One is, yes, they have limited resources, they don't have a lot of data. So we wanted to demonstrate the value of this Pipe ID and to collect the data at national scale. Now we are working with Houston, with Denver Water. We are trying to reach out in Denver Water because we have data from Denver Water and all those. What we are seeing now is that up to 50-mile, 100-mile radius, we can provide that for the small utility because a lot of those data will be valid. I'm not saying exactly the same, but a lot of these data which can be downloaded from USGS and all those. So even if a small utility have basic, like 5 parameters, when they put the pipe in the ground, they don't have to have, I mean, they can also use some, like all data in our database, we are coding in 3 ways. I didn't explain, I saw the one question is there, how you know this data when it runs into the model. So all input data we coded into 3 categories. One is direct observation, second is derived, and third is educated guess. What's the difference? Direct is the direct measurement. That means they went and took the soil and all those. Derive is what we learned from Pittsburgh is a lot of slope they derived. But when we did hydraulic analysis, we realized that's not right. They said that hydrant A is at this elevation, hydrant B at this elevation, so pipe is connected in a straight line. That's not true. Pipe was running like 30 feet horizontal, then it dropped. So that's a derived data. Educated guess, you don't know soil, you are guessing that it may be, or bedding it may be. So you don't blame a model. Model is just a digital filter. So right now we are working very hard to engage a small utility. That's the plan this year. So how to engage a small utility so that they can also start using this digital platform for Pipe ID, especially for Pipe ID project.
So Elkin, I can chime in on that. If you have
Sure,
time.
please.
So what we did when we started about 4 or 5 years ago, really trying to use the data, is we did what Jim said, we did a value map. So he looked at our work execution process and who was putting the data in, who was using it, and what value that brought. So are we driving a KPI? So we looked at our KPIs, how they're being calculated. So there's a lot of reliability KPIs, mean time between failure, return on investment, other things like that. So we looked at which ones we could use. And so kind of what questions are you trying to answer? And then build and try to emphasize that data being good. Because we have a lot of data in the system, but again, not all of it's good. So we really focused on what questions was maintenance trying to answer? What questions did operations want to know? And trying to really emphasize on gathering that data and making that a highlight so that when we did get to the point where we could answer the questions, we had good data to begin with. So what questions are you trying to answer is where I would start.
Certainly that's the case, and certainly it's important to recognize the challenges for small utilities, not only on the smart water front, but as we know, and we're aware on the cyber front as well. The resources and their challenges are sometimes a bit different.
Yeah, and to explain to people how you're going to use it, because a lot of times people think asset management is we're just spying on them, collecting data, and if you can explain how you're using it, then they're a lot more buy-in because they're very suspicious of why you want this information.
From my personal experience, I think it's a journey. You may and to get to a point where you have actionable data that can be used can be reliable and trusted. Most of the time, you have to build those tools and that data sets and the QA/QC processes to make sure that it's consistently there and people start trusting it and relying on it to make decisions. At the end of the day, is how what is the value that it's bringing and how it's making people's life and decision making better. I have a question that goes into the same framework. Is how do I calculate my return of investment in the data-driven asset management sector? So, any thought there, perhaps, Jim?
Sure. So it's nearly impossible to answer that with one answer, right? You really need to, as Theresa mentioned, look at establishing KPIs for your various aspects of your utility, and that can vary from hundreds of KPIs for a large utility to a couple very simple ones for a small utility. So I guess the way I'll answer that is if you can't or if you're not measuring it, then you can't monitor it, right? And if you're not monitoring it, then you can't improve it. So it really comes down to making sure that you're collecting, again, going back to what I said, collecting the right data that you need to drive and look at and monitor those KPIs so that you can improve them. And the question about small utilities versus large utilities, I think large utilities out of necessity have a very more mature data structure or schema. On smaller utilities, that's probably, at least what I've seen is a bit less focus on the data structure that they have, just because they don't have hundreds and hundreds or thousands and thousands of tags and assets that they need to monitor. So, even if you're the smallest utility and you have a few assets and one treatment facility, still have a structure in place so that you follow it, so that at some point in the future, maybe, long distance, maybe 10 years out, you can go back and say, hey, look, I have 10 years of historical data right here in a structure that we developed. So I think that's really the important step.
Thank you, Jim. So, and this question, we have touched the point of data quality several times, but I'd like to make a question here related to the quality is, do I need perfect data to make decisions?
I'll start with that. I'm sure others can answer too. It's one of the topics I usually bring up for this first question. What are the biggest challenges? Sometimes utilities think that their data is not good enough to be used to make improved decisions. If you're waiting for perfect data to begin doing things like AI, then none of us will be here, right? Because you'll probably never, ever have perfect data. right? The question is, what's that balance of what do you really need to get there? And you know, so the answer is no, you don't need perfect data, but certainly you need some sort of structure and you need some sort of baseline data, right, to really get going. And if you don't have that, then you need to build out that data set. You need to do the work to identify what it takes to get that data. A good example is we were looking at trying to apply a data-driven asset management to Flint, Michigan, and Flint did not have water age, or excuse me, install years for their water pipes, right? So we had no age data for the pipes. And we said, well, how in the world are we do this? So we basically created a GIS process that went out. First, they went out and wrote down the install or the manufacturer date for all the fire hydrants in the system. And then we had a GIS process that looked at within any given stretch of pipe, apply the oldest fire hydrant date to that stretch of pipe, right? So there's a lot of processes you can do to kind of build that data set. Certainly it's not going to be perfect, but it's better than nothing, and you need a starting point to go from there.
Thank you. I have another question that I think can be important here and relates to the maintenance aspect of this business. Is so most people would say, I have a system that works using a schedule and preventive maintenance. Why would I want to change? Why would I want to do things differently? Any thought, team, perhaps?
Sure, Elkin. I think, you know, whenever we think about this is always a challenge, right? This was change management that we've sort of talked about. We have a process that we understand and we're happy with. And so often we stick with what we know rather than looking at the potential advantages of what we may achieve. So when you look, and Theresa could probably talk to this as well with her Blue Plains example, if you start with, we go way back in time, you have a Rolodex of little flip cards that write down the date you installed something and when you serviced it and what it cost. And then eventually you put that into some sort of data structure. And then we run every year, I go out and do X to a pump. The cost of just doing X to a pump on a routine, regular basis is probably much greater than doing it based on a data-driven approach where you're analyzing the data that the equipment is providing to you to make assessments about when to maintain it. So if I can deploy more people within my utility more effectively, rather than doing routine tasks that aren't necessary, I'm obviously going to realize cost savings down the road. Hard to change sometimes up front, and it won't always work. Things may still break down sooner than the data tells you. It just happens. But making that shift should result in cost savings over the long term. So again, transition, change management, process management, you know, it's a process though to get there.
Thank you, Tim. So go ahead, please.
Yeah, one thing to add on to that real quick too, I want to make important the distinction that you know, I'm sure the other presenters as well are not advocating that if there's a great shiny object out there that you go for it, right? I often tell utilities that if you can achieve a similar result to using AI by a simple solver in Excel, then by all means, you should be using that solver in Excel, right? We want to keep it as simple as possible to get the right answer. But don't let that stop you and at least explore what the possibilities are of using AI. If they don't give you good results or the same results, then don't take that more complex solution, right? Go with what's simple. I think what you'll find though, and what the data has shown for utilities that do it, is that you will get a better answer. You will have better cost savings with some of those approaches.
Thanks, Jim. So I have a question here, and it goes into, if we define the parties for this type of initiatives, data-driven asset management as being a utility, you know, consulting firms and IT providers, what do we think we need from each other? What does the utility need or want from a consultant firm or from IT? Theresa, do you have a thought on that? From your utility perspective?
Yeah, so that ties into the roadblocks that you first asked. I have one place where I want everything. Sometimes to get an answer, I have to log into 10 different databases. So to get my IT providers to be able to easily give me the data so that I can manipulate it next to Scada, next to the lab, next to the, I love that my IT providers that do my vibration and ultrasound have these great, and oil analysis, have these great websites that do beautiful graphics, but I want it next to my other graphics. So just being able to be flexible in giving me the data so that I can look at it with my other 12 things that I need would be something that I want.
Okay. What does IT want from the utilities and consultants?
If you're asking me, representing the software company here,
Yes.
First of all, I think there's two examples come to mind that I've experienced over the last couple of years. One is utility in Georgia, and the other one is utility in California. And the Georgia utility I started talking to almost 2 years ago, just when I joined, and nothing has happened until now. They're just like analyzing and analyzing and analyzing what they might need to do in the data driven world. And there's a lot of ideas and a lot of good stuff. It's just not doing anything. And the other one in California, I already had some providers, and they said, you know what? We have this area, the distribution network, we haven't touched it, or the treatment plant. Let's just start doing something. Let's just think about it. So I think this just do it versus analysis paralysis mentality is the one thing I seek. So, just pick a pilot, start doing. You can analyze yourself to death and not do anything. Like I see in this Georgia example, still nothing. It's amazing. Versus the other way around, and the same size, more or less. Same, there shouldn't be any difference. So going back to the beginning, the culture, the barriers, mental barriers maybe. So that's my expectation, and I think it goes on with kind of like actually implementing, working side by side, and that what drives value in the end. Naturally, you need to have a vision, you need to have a clear design, but just the just do it piloting mentality. There's so much to do. There's so much to do. If you want to analyze yourself to death, you can, but you'd rather just do it, So that's my perspective.
Thanks, Guy. Anybody else has a thought there? All right, so I just got we got a very interesting question. I think we need to jump to this one. It says, are there any notable gaps or deficits in utilities' ability to gather data today? Data that would be viable to have, but where capability to gather is too expensive or just unviable? What is that magic data set that we like to get? Anyone with a thought there?
Elkin, I'll just comment. We've seen a huge explosion in the ability to collect data. Data has not stood still over the last number of years, and we have gigabytes and gigabytes of it, and the cost of collecting and bringing data together is going down and down and down. When you look at the IoT platforms that bring data from remote locations in now, very cost effective communication over cellular, even 5G is just going to help that. You start to actually look at it. I would say Jim made a point about there's certain data that you never look at. So why are you collecting it? Reallocate resources to collect the data that you are going to actually use. And you may find that the costs are not that significant. The other thing I'd always suggest to people is once you know the type of data you're looking to collect, every time you have a capital project, make sure that the data you truly need is embedded in your capital projects so that you start collecting it and you start building that baseline of data that you need to go forward. So yes, there are hard bits of data collect. Is it insurmountable? No, I think you can get access to pretty much any of the data that you want nowadays.
Thank you, Tim.
One challenge for, go ahead, one challenge
Theresa.
we had with documentation. So the planners and the foreman want to know, well, what part is on this piece of equipment? So I mean, our plant's from the 1930s, and we still have equipment that's been rehabbed a bunch of times since then. So I don't have the original service manual from 1930s. It's probably in the Smithsonian somewhere. So where does that information and how? And so in 2000, we started, like Tim said, all of the new construction projects, service manual had to be scanned in, and then they had to have certain things in them that the planners needed, exploded views, spare parts. And then our Maximo asset management system, actually, that asset links to that service manual. So we still don't have 1930 to 2000 scanned in and documented. That would be very expensive and unavailable, but it helps if you have that information. You know you're going to use like service manuals, spare parts, stuff like that to just start somewhere.
Right. Elkin, can I add just quickly
Please.
on that? So let me give you a horror story. So in the Pipe ID project, when we started collecting data, what we found is a lot of data. It's not like you ask the utility, give me pipe data, and they will burn a CD and hand it over to you. I wish that, but it didn't happen. Data came from many silos within even the department, like Houston, big utilities, many financial department, operation and maintenance, construction, their soil report came from different. So there are many silos where we have to go and reach out and collect those data. The other challenge is the utility data is a lot of GIS. Let me go with GIS. A lot of bigger utility, they have GIS. GIS data, you cannot rely. Data is not black and white. When we got data, I will just give you one example, a lot of failure from ductile iron. Let me give the example, ductile iron, line ductile iron, lot of failure. When students analyzed the data, they said, Dr. Sinha, we are finding a lot of failure in this pipe. I said, that something is going, let's check with the soil, let's check. We checked everything. We couldn't figure it out. There was no correlation. Then we went to that utility, and then the GIS guy who was in charge, he said, Sunil, you are talking more technical, let's bring the whole team and all those. When the discussion took place, one guy brought that, oh, this pipe was not factory lined. This pipe was lined after 20 years in service, but all break record was carried over. So my point here is we are talking a lot of data. Data has a physics behind it. Data is not black and white, and not understanding what AI or any math will do, nothing. So the key is not just the data, understanding where this data is coming and how you are getting this data so that we can use for analytics. I wish I would have spent more time in analytics than cleaning the data, understanding the data. So that's my last comment on this data.
It is certainly important to remember that there's still people behind making evaluations and making sure things make sense.
Right.
We're not yet at a point where a machine can get all the water data
right, exactly.
Right away. We still have to have a human.
Yeah, we are not aerospace industry. We are not medical industry. We are.
And I think that's a good thing for now.
Even in the medical industry, you still need the physicians to interpret the data.
You'll be surprised how.
One of the sectors that I worked for in the past was not successful in that at all, I think.
We still need it for now. That's good news, hopefully to everybody. So we came to, we run out of time. It's 3 p.m. I just want to say thank you to the panelists. Thanks for devoting time and an effort for this presentation. I want to thank all the people that participated on the webinar, and hopefully you guys can join us next month for the next webinar for this data series with WEF and the Cleveland Water Alliance. Thank you.
Thank you.
Thanks everyone. Bye-bye.
Thank you.